They work great for jokes too. All right. Good morning, everyone. Lab day. So we're gonna finish up. Last class we did momentum. We did a bunch of conservation momentum problems, and then I started teaching you all center of mass, and we did this example of GPA to get a sense of it. That if you were comfortable with this idea of how your GPA is calculated, center of mass is the same exact thing, and it's just reaching a place where you're comfortable with that connection. Because I think you all are cool with GPA calculations. I think so. Maybe not. I don't know. But I think it's a great example. And then center of mass is the same thing, just you do it in the X and you do it in the Y. And instead of GPAs and credits, it's your X position and the mass divided by all the mass, or their Y position times mass divided by all the mass. So we're going to practice 2 problems today. It's actually the only 2 problems I have in the problem set. If you want more, we can figure out more. But we're going to do that. Next week's lab will actually be on center of mass. This week's lab will be on momentum. So you'll get even more practice next week. But yeah, so we'll do center of mass, finish it up, and then we'll start to talk about fluids, and we'll finish fluids up next week. Fluids, I'm excited to teach fluids because it's something that this is going to sound really weird. I've never actually had a course on fluids. You're like, wait, why is he teaching us this then? Physics is physics. The reality is the process, and that's what I hope to convey to you all. If you learn how to do this stuff, you can learn any physics. And you can learn any physics and then teach other people the physics. It's all the same process of drawing pictures, what's given, what variables. So with fluids, we're going to work with forces and areas, velocities, variables that we've been working with. Just in a new context, and there's a lot of cool, fun stuff in it. Yeah, so it'll be fun to teach. There's a lot of consequences of it. I can teach you how hydraulics work, which may be like, why do I care? So many things use hydraulics. It's great. Anywho, whatever. All right, Peter's got the joke.
Why couldn't the pepper practice archery?
Your mic cut on. Halfway.
Why didn't the pepper practice archery? Because it didn't have an arrow.
Have an arrow, like the pepper? That's good. Well, that was good. That was a good synced up. I never get that with teaching physics. Anywho. There you go. That's a good one. Okay, so center of mass. Again, we're going to do 2 problems, and we're going to start with this. We're going to start with a 1-dimensional center of mass, and then we'll do a 2-dimensional center of mass. Then don't worry, you're spared 3-dimensional. Center of mass, again, super, super useful, just to convey to you all the benefit of center of mass. Remember, it's basically you can take a whole bunch of crazy objects, and you can kind of imagine that you squish them to this single dot. That's the benefit of center of mass. Like every projectile problem that we've done in this class. So remember I showed you all this video where they tossed stuff and it looked all crazy when you could see the object, but when you looked at the center of mass, it was a nice parabolic path. Every single projectile motion problem we've done in this class, you've just been tracking the center of mass of the object. You didn't care whether it was spinning, you didn't care the shape of the object, you didn't care whether it was a piano. You just, without you even realizing it, you were doing center of mass. Another example of center of mass is your all's car tires. So this is a foreshadowing of next week's lab in a little bit. Center of mass is about which things rotate. So if you have something spinning, it's going to want to spin around its center of mass. And so why is that important? If your car tire, the center of mass is not perfectly centered, your wheel will wobble, let's say. You're going to get vibrations. If you all ever get your tires done, they do something called balancing your tires. Literally what they're doing when they balance a tire is they're shifting the center of mass to the middle of your tire. If your center of mass of your tire is anywhere other than that, it's going to want to rotate around that. And just to draw a quick picture of why that's bad. If you have a tire, random slide. If you all have a tire, great. Where do you want the tire to spin? Where's the axle connected? The middle. If your center of mass is over here, your tire is going to want to try to rotate around that, and it's going to put some strain on your axle. Your tire is going to want to rotate about this point instead of the center point, and that puts strain on it. That makes it unbalanced. That makes it throw, like, it'll be really bad for your car. Basically, when it's on one side, it's going to pull one way. On one side, it's going to pull the other way. And eventually, that's going to break your axle. And it'll make your car ride really, really, really rough. So they put little lead weights. If you all look inside your tire, depending on your car, you can actually see little lead weights kind of glued to the inside of your tire. And they do that to center, to shift the center of mass. So anywho, it shows up. It's relevant. All right. So this first problem is going to sound all crazy, but once we draw a picture of it, it'll be fine. We're going to find the center of mass for the Earth-Moon system. You got two objects. We can find the center of mass of those two objects. We're going to use the Earth's center as the origin. The mass of the Earth is 5.97 times 10 to the 24 kilograms. The mass of the Moon is 7.36 times 10 to the 22 kilograms. And the distance from the Earth to the Moon is 3.85 times 10 to the 8 meters. If the radius of the Earth is 6.37 times 10 to the 6 meters, how far away is the center of mass from Earth's surface? Again, it's like, oh my gosh, so much information. Draw a picture. Draw both objects. Draw where your origin is. The origin is where we're measuring distance from. You get to choose the origin. We're going to pick a spot that's really convenient for us, though. So pick where you think it's convenient to pick the origin. So anyway, draw the Earth, draw the Moon, pick the origin, draw numbers on the thing. This is going to help us out.
This is center to center distance?
Yeah. That distance is center to center. When it says distance from the Earth to the Moon, it's center of the Earth, and the center of the Moon is that number. Oh, that's a good point. Second to last one in momentum. All right, number 15. All right, so you got two objects. There's the Earth. There's the Moon. Doesn't even matter if you draw them the right size. And then we know the distance between them. I give you that. 3.85 times 10 to the 8 meters. Okay, and now we're going to choose where y. Remember, in almost every physics problem, you kind of get to choose where the origin is. In this case, we're just working left-right. We're going to choose where x equals 0. And we're going to choose some place that makes our life really easy. Do y'all have any guesses? So left-right is where we're going to choose. Yeah, that's a great point. We don't have to worry about y in this case.
The part closest to the Moon.
Right here?
Yeah.
So we could totally choose there. That works. Any other ideas? No answer is wrong. Center of the Earth, that's another idea. Any other ideas? I'm going to collect all the ideas, and then I'm going to show you all the process, and it's going to help us see how to choose the one that makes our life the easiest. No idea is bad here. Just some are like quicker. All of them will work. Any other point? There is another point that can be convenient. Yeah, you can do the center of the Moon. All right, whatever. So that's where we're gonna pick one of these dots, and that's gonna be our 0. Everything's gonna be measured with respect to that dot. That's our 0, 0. Remember, we have to have a reference. Remember, one of the first questions I asked you in the class is, where is Bulbasaur located? And you had to decide you had to decide what you're measuring with respect to. From where? So, we got a bunch of things. We'll make a nice little list here. Mass of Earth is 5.97 times 10 to the 24. Unfortunately, we didn't do universal gravity, so universal gravity, we would have looked at this more. But something I just want to mention while we're looking at this number, when you work with scientific notation, sometimes it can kind of hide how big or small something is. So I don't know if y'all have ever done that. You might not have ever seen this number before. This is the mass of the Earth, 5.97 times 10 to the 24 kilograms. I'm just going to write out this number in its entirety just so you have a sense of how big the Earth is. Because it's something that, again, when we work with scientific notation, you can sometimes just be like, it's a number. Let's actually write out this number. It's 5, and then I need to move this decimal place 24 times to the right. So 9, 7, that's 2 times 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24.
How do they calculate that?
Oh, what a good question. How do they calculate the mass of the Earth? Oh gosh. Do you remember, Peter, off the top of your head? If not, it's going to take me a few moments.
So, I do know the way they get average densities has to do with observing orbital interactions. And then if they have a good idea of the size, they can get a mass from that.
So there's...
like they do that with asteroids.
The one way... Okay, so I haven't taught you all 2 things. One is universal gravity, which we're not going to cover. Which is, I know, very sad for you. That you're not going to get to see the equation. So it turns out that the force of gravity is G m1 m2. You don't need to know this. That's the equation for the force of gravity between literally any 2 objects, the sun and the earth, 2 dust particles in space, 2 astronauts floating in space, 2 of you sitting in this room right now. All of you are attracting each other, as weird as that sounds. Your mass is just nowhere close to the mass of the earth, so you don't notice. So that is if you're ever self-conscious about your weight, you never have as much mass as the earth. Nowhere close. Use that as your reference. So, anywho.
Also, the capital G is not 9.8.
Yes. Yeah, that's just a number. It's 6.674 times 10 to the minus 12, I think. Why do I know that? Because I taught the class and had to use it a bunch, and I'm still probably messed up something. Anywho, it turns out, and we're going to learn about centripetal force. If this is the only force acting on something, we can set this equal to mv squared over r. And you can actually, if you watch how fast something is orbiting a planet, and you know how far away it is, with this simple equation, you can figure out the mass of the planet, which is crazy. It's a really cool problem that sadly we don't get to do in this class. But literally, yeah, you can just look at a planet, see how fast a moon is going around it or a satellite, know how far away the satellite is from the center of that object, and literally this is the only equation you need to figure out the mass of the planet, which is wild. It's such a simple equation to figure out the mass of literally any planet, star, anything, which is super cool. But yeah, sadly, I didn't teach you all the first equation, so we can't do it. You'll learn the second one, though. Anyway, this number is nuts. Again, to give you a scale, there's your mass. About 70 kilograms, give or take. And what even is this number? There's a million, billion, trillion, quadrillion, quintillion. I don't even know what the names of these. Yeah, septillion maybe. I always mix up the 1 for 7 and 6. It's stupid big. Yeah, the Earth, you often see pictures of it. Obviously, you all know the Earth is big, but it's really hard for you all to get a sense of how big the Earth is compared to you all. And that's just one planet, and then there's billions of planets and stars, and the universe is nuts. Anywho. Sometimes it's good to kind of see that stuff as a reminder that while the stuff happening in your life matters and is significant, the universe is so mad. Sometimes stepping out and be like, man, so much is happening. It can sometimes help you kind of reduce the pressure on whatever you're experiencing. Sometimes. Other times people can go the other direction and say everything's meaningless. Who cares? Whatever. Try not to end up in that direction. Everything is not meaningless. You matter. All that good stuff. All right. Whatever. That was my complete tangent that had no physics to it other than big numbers are big. Great. There's the mass of the moon. And then we have a distance. I'm not going to write the distance in the givens yet because we actually need to choose an origin for us to write it down as anything useful. We're solving the center of mass. So which dimension are we working in? X, Y, or Z? X. We only care about left, right. The center mass of the Earth, though, and the Y direction will be dead center. The center. We only care about the X. You got two objects. They're both in the same thing. We're going to care about Y when we have a problem like this, which isn't that, like, don't freak out. It's not that bad. This problem, you have objects in the X and the Y, so we'll have to do both. That's the next one because it builds on it. Great. So we're just going to do X center mass. So all we need to do is multiply where each object is times its mass, and we're going to add those up, and then we're going to divide that by all the masses together. So we have two objects, so we're going to say where are they times their mass, add the next one, where is it, times the mass, and then divide by all the mass. Yeah.
For the first mass, like on top, is it just the mass of one of the objects?
Yeah, so there's technically like a little index here where you're summing over however many objects you have.
Okay.
So position 1 times mass 1 plus position 2 times mass 2 plus position 3 times mass 3 plus.
So is the masses on both of them going to be the same number?
That's a good question. So it's going to iterate. So think of remember this equation. So these are great questions. And the way I'm going to remind you all how we're going to use this, so I'm going to support you all in using this, is remember it's like this. Remember it's like this whole GPA and credits. Each class had its own GPA and each class had its own credits. So we multiplied those two. Then we added the next one. Then we added the next one.
For each object, the mass of that object times the x coordinate of that object.
Yeah. So I'm going to help you all out building this because this is the first time. The best way to see how to do center of mass, because it is just a single equation. Like there's no nuance to this. It's just use this equation. So the best way to do these problems is just to see how it works. So let me write this out. We're going to do the x position of object 1 times the mass of object 1 plus the x position of object 2 times the mass of object 2. If I had 7 objects, I'd just keep doing that. Plus x position of object 3 times mass of object 3 plus x position of object 4 times. Great. And then you just divide that by the sum of the masses. Mass 1 plus mass 2. So this is how you do center of mass. You just, where am I located times my mass, plus where am I located times my mass, plus where am I located for every single object you might have. If we learned calculus, I would then eventually teach you all, if we had an infinite number of objects, we would integrate it. An integral adds up an infinite number of things. But we're not. You're spared. This is all you have to do. Okay. Now that we see this equation, remember these x's are where I'm located. Where am I located? From where? Where's my reference? You're always measuring from some reference. And so what I want to show you all here now is depending on what reference you pick, your life gets much easier. If I pick the origin as the center of the earth, how far is the center of the earth from the center of the earth? 0. So if we choose the center of the earth, x1 will equal 0. It's where I'm located with respect to it. If I choose that, what's x2 going to be? Where's the moon located with reference to my origin? Yeah, the distance there, and it's nice and easy. So this is probably the easiest one to pick. Pro tip, every time you're doing center of mass, choose the origin as one of the objects. Just pick one of them, then you have less math to do. So this is one. This is then going to be that 3.875. I just want to show you all the other one. What if instead you all pick the moon as the center of mass? Here you have to be careful. If you pick the moon, and we're gonna choose the Earth just so that y'all know. If the moon is the center of mass, where is the Earth located with respect to the center of the moon? Negative 3.85. If you all chose again, I'm going to write this and I'm going to immediately erase it. I'm just showing you all two examples, but I'm only going to pick one, but I'm just showing you both. This would be negative 3.85, blah, 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 because it's to the left. If you don't use positives and negatives, you're not going to know whether the center of mass gets shifted left or right. We need positives and negatives because it matters which way it's located, left or right, relative to the origin. So anywho, whatever. We're going to choose the center of the Earth. That way we don't have to deal with the negatives. So we're going to choose here. We're going to call that the origin. I'm going to rewrite everything I just erased. So that's going to mean that x1 equals 0 because the distance from the center of the Earth to the center of the Earth is 0. That's going to mean x2 is going to be 3.85E8. And then go ahead and try it. You all can do you all have the skills to do the rest of this. Just put the right masses in the right places, plug it in, solve. Get the center of mass of the Earth-Moon system. It is not the center of the... Oh, and this is where they both orbit around. The center of mass is what both objects actually orbit around, which is kind of cool.
Yeah, I got 4.7.
And then if you get part A, do part B. That's just reasoning, logic and reasoning to get part B. Oh, when y'all get this answer, draw it on your picture. After you do part A and B, draw where the center of mass is on your picture. Not that you have. It's just a cool thing to see.
Center of mass. Earth-Moon system.
Is that working? There you go. Big. Did you go the right direction? Oh, I see.
So your first answer is so you know how big the radius is? So you just subtract the radius from because it's two-dimensional.
That's nuts. Your setup here looks good. I think you multiplied things higher. Because the reason everything you divide, you're effectively subtracting. Yeah. So your setup there is, if this looks basic and that's off, then it's probably because you flipped something else. So when you divide, so what I recommend is instead of using the times two notation, you just divide. So what you did in your calculation, you divided this by this number, and then you If you do the time spin, if you use the E button instead, you actually don't have to worry about it. It automatically does it together. It's just a convenient calculator.
So, if that's radius.
All right, I'm starting to plug in the numbers here. So the distance of the origin of the Earth is 0. So that times the mass of the Earth is 5.97 E24 plus the distance to the Moon from the origin, 3.85 E8 times the mass of the Moon, 7.36 E22. I highly recommend you all find on your calculator the E button, that capital E button. There's many ways to do scientific notation in your calculator. But one really common mistake is, so on the bottom here, we're going to divide by both masses. If you use the E notation, you don't have to be as careful with parentheses, which is nice. So, I mean, you do have to, like, add them up first or whatever. You still have to do parentheses in that sense. But the E notation is great. Your calculators use it. If you ever do any programming, you're going to do scientific notation, and most programming, E is how you do scientific notation. So there's a reason I use this notation when writing out problems. It is shorter for me to write. It's what your calculator uses. It's what's if you're doing any software programming, it's what it uses. I don't have to do a superscripts and subscripts and all that jazz. It's just a little bit more efficient, but you do you. When you all get to physics 2, you are going to do a lot of this, a lot of scientific notation, because you're going to work with really small stuff. Times 10 to the minus 6, times 10 to the minus 9, times 10 to the 9 for one of the constants. Anywho, so there's the answer. Now the next question is, how far away from the surface of the Earth? So obviously the surface of the Earth here, there's a lot of different points. It wasn't clarified, but I'm talking about the closest point, which is going to be there. So, you know, like I mentioned, when you did part A, what I wanted you all to do is actually draw on the Earth where the center of mass is. And honestly, to draw where the center of mass is, well, if the radius is 6.37, so the radius here is 6.37, and my answer is 4 times 10 to the 6, so the same order of magnitude. It's going to be about 2/3. So the center of mass is going to be about here, 2/3 of the way. 4.64 is almost 2/3 of 6.37, kind of, sort of. Again, so the really interesting thing about this is the Earth and the Moon. The Earth actually orbits this spot. So as weird as this sounds, the Earth is orbiting a spot kind of inside it. So you can almost think of it like spinning around that spot. When the Earth and the Moon are spinning around, they both orbit around that dot, which is a weird idea. But a more extreme example of this is if you all had like 2 stars, they would orbit some spot in between the 2. Yeah.
Is that why Earth is on an axis?
Oh, that's a more...
No.
That's more
The
complicated.
short answer is no.
Yeah, that's a great question. The question was, is that why Earth's on an axis? That's more how the Earth got spinning in the first place.
So you had, at the very beginning, you had sort of a giant cloud of gas and dust, and slowly collapsed, condensed into. You had the sun in the middle, and then you had planets forming. And long story short, the cloud had some angular momentum to it. It was, on average, spinning. And so you wound up with the sun spinning and the stuff around it orbiting and also spinning. And so, but planets will usually be spinning whether they have satellites or not.
Yeah, there is some planets that are called tidally locked, I think.
Yeah, and so that happens when tidal forces slow down the spin to match the orbit. So it rotates once in the same time it takes to make one orbit. So the moon is tidally locked to Earth, which is why we always see the same side of the moon. And tidal locking also comes up a lot studying exoplanets. Because you have like a really big planet that's really close to its star, it will usually be tidally locked. Even small planets really close.
What about the slant though?
The dust just happened to be spinning at a slant or something.
But yeah, the tilt is usually because of like an impact or something.
Maybe it was right up at one point and then someone smashed into it and tilted it slightly.
So that's the leading hypothesis for how we
Interesting.
got them in the first place.
Yeah. Oh, yeah. Cursigeist is great. I got a bunch of posters in my room. Again, there's a lot of cool space stuff. We don't get to too much of it, but what's really cool about space stuff is you get to ignore air resistance in space. So, like, a lot of the physics for, like, the big planetary bodies is very simple. A lot of physics was actually discovered by looking at planetary bodies, and you get to ignore a lot of complex things. The universal law of gravity was discovered by looking at the moon and like various things like that. So there's this has nothing to do with it. Helium was first discovered on the sun before it was discovered on Earth. And then you're like, what? But I've never been to the sun. Because there's other ways you can get information other than physically interacting with something. So that's a fun thing to kind of look up.
Another fun space fact for the day: if you do this calculation for the Pluto-Charon system, you get a position that is outside of the surface of Pluto.
And Charon, I assume, is one of the moons.
It's the one.
Okay. Yeah. So again, cool stuff here. Be curious. If you all ever if you're like, man, I like physics stuff, but man, I don't want to do it. Like after this class, I don't want to do any more math. Cursigeist is one of my favorite YouTube channels for like science stuff. They do a lot of cool space things. There's not any math, so don't worry, it's not scary. It's great, where you get to enjoy learning the physics with maybe not having to hurt your brain as much. Don't stop being curious. The second you stop being curious is when your brain goes stagnant and you stop learning anything new. And it's very sad. All right, the radius of the Earth, I need this for the second part. I keep jumping back and forth. 6.37 times 10 to the 6. 6.37 e to the 6. So for part B, if you didn't figure it out, how do you figure out how far away you are from the surface? You build the equation. This one, there's not like you just subtract the two numbers. And you can see it from our picture. If I want to figure out this little distance, let's call it this little blue distance here. You just subtract the radius of the Earth from this number. Well, this number from the radius of the Earth, and it all works out. It's more of a little logic puzzle than any physics. When my eraser stopped working. All right, I give up. Big old minus sign. Equals, the answer is 1.68 E6. If you're wondering why the answer is negative, it says, the question asks how far away you are from the center. From the surface? Am I to the left of the surface or to the right of the surface? If you all look at your picture, here's the surface. The green dot is where I'm located. I am to the left of the surface. So it is 0.68 E6 from surface. Why? Center mass is to left of surface. These are vectors. We care about left and right. We care about up and down. We care about which way the center mass is going to get shifted. So we need to care about positives and negatives when we're doing these problems. We care about direction. Anytime you all care about direction, vectors. Anytime there's a problem where it says like any aspect of it you care about direction, vectors. Energy, there is no direction. I've never asked you in what direction is the kinetic energy because it's not a thing. All right. Oh, everything broke. Yeah, I hate when it does this. All right. Go ahead and try the next problem. I haven't had to do this ghost thing in a long while, but here I am. So I just have to close this and reopen it. So the next problem is 3 objects. Find the center of mass. The only challenge there is you all got to do it twice. In the x direction and in the y direction. You need to find the x center of mass, so only use x coordinates. And then you got to find the y center of mass and only use y coordinates. That's the key to doing that one. Do one at a time, though. Why is that there? Oh, I told you what the origin is. I spared you, well, like, for good or for bad, I told you use the 150 gram object as the origin, so that way we all get the same answers.
That's yours to feed. It's 100 centimeters.
Me? For the x direction? Okay.
You still want to do all three objects?
Okay.
So this one still, you do the x coordinate, this one, x coordinate, this one, x coordinate.
Oh.
All three of them.
Okay.
Yeah. Now, it is kind of nice. What is the x coordinate of this one?
0.
Yeah.
Okay, so you would just
You
have
just
that
Put
in
the
this.
mess,
Okay.
Yep. So you want to find the x and y coordinate of every single object. That's kind of one of the first steps in this. Where is each object located, x and y? You're going to need that information. And everything is measured from the 150. We said that's our origin. So what's the x and y coordinate of every single, there's 3 objects here. On the picture, add those x and y coordinates for each object. You're going to reference that. You're going to need that information. But is it lamer or less lame than everything else?
Yes.
It's both?
Yes.
Well, I mean, that averages out to be the same. It's at least very straightforward.
I think kinematics was lame. That was like 5 equations. This one's only 1 equation.
And kinematics is one of those, it seems really bad at first.
Oh, I think so.
It's bad if you feel like you have to memorize them all. Yeah. But they are like the most, kinematics are like the most straightforward problem. It's just like,
Yeah, but I remember how to convert it to time. I hate doing
it's converted to time.
that. How did it solve?
Oh.
I hate doing that. But no, I wrote that
And then that's divided by 4 plus 4.
So yeah, when I'm going around, I'm going to be looking to see if you have these coordinates down. That'll be my way of like checking how it's going. Yeah. Awesome.
Yes.
Oh.
Oh, okay, yeah.
So what's its x and y? Where is it? How far is it from the one? And then what's this one's x and To give you all a sense of this xy, basically like make a coordinate axis. The origin is the center. If you're trying to make the x and y position, make a big old coordinate system where the center of it is there. What is the x and y position of every object? That's the key to, like, that's one of the first steps with doing this. That's something you're going to need. So, I like to label these objects. I'm going to call this guy 1, this guy 2, and this guy 3. Whatever. It's just going to make my life a little easier when I write out the equation. What is my location of object 1? How far is it left, right from the origin? 0. How up or down is my 150 gram object located? 0. Great. What about object 3? How left, right is that object? 0. If you really want, you can make it -0. What's my y coordinate? 3. Now, something that's kind of nice about center of mass, I haven't mentioned this. Center of mass is one of the few cases where you can leave things in centimeters if you want. If you want to play it safe, though, I recommend, if you don't know why this is true, just convert it. Just convert it to meters. Make your life more consistent. If you don't know why you can leave it in centimeters, it's a good practice just to move it to meters. That will always work. All right, the last xy coordinate. Where's object 2 located?
4.
-0.04. If you don't put the negative, you will get the wrong answer. And what's my y coordinate of object 2? 0. You need the xy coordinates of all the objects. Also, you don't technically have to convert from grams to kilograms for center of mass. If you don't know the reason why, just convert.
I have a question. I didn't convert from grams to kilograms, but I still got the right answer.
It's because you have the mass on the top and you have the mass on the bottom. All the units end up canceling out for mass.
Oh, okay. So you don't have to actually.
Yeah.
Okay.
The units all cancel out for mass, and all you're left over is the units that you used for a position.
Okay.
So it'll be whatever units you used for that.
Okay.
That's the reason.
Grams divided by grams is 1. Kilograms divided by kilograms.
These types of problems you don't have to make it to kilograms.
Nope.
As long as you keep track of what units are.
Okay.
Yeah. As long as you keep track, and as long as you don't end up mixing it up in other problems.
Centimeters times grams divided by grams, you'll wind up with centimeters.
Okay.
Centimeters times grams divided by kilograms, you're going to wind up with a mess.
Yeah.
Okay.
You're saying 0.03
And if you're
centimeters.
doing meters times grams divided by grams, you're going to wind up with
Whatever makes it.
So then, yeah, center mass problems are all the same. Figure out the xy coordinates of everything, and then just find the x center mass and find the y center mass by taking each object, multiplying where it's located in the x times its mass, plus the next object, plus the next one, plus the next one, plus the next one, and then you divide by all the masses together. You want the y center mass? Take the y coordinate of one object, multiply by its mass, plus the y coordinate of the next object times its mass, plus yada, 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 yada. Go, go, go. However many objects you have. And if you had 1 million objects, this would let you get the center mass of 1 million objects. That's the power of it. And this is where if I threw this thing through the air, it would spin about this spot. If this system was all connected together and I threw it, it would spin about this spot. If I wanted to place if these were all connected together, this is a rigid body. It's where I'd put the support column underneath it to hold it up. All that kind of jazz. Yeah, now we'll just go around. If you're not sure how to set it up, call one of us over. I don't want to give too much money, so it's not very interesting. Sure. So you have how many objects? So you gotta do all three of them. Even it doesn't matter where it's looking up. You add up all of them, and then you divide by all of these. And the reason is, even though this one's on the Y, it's gonna shift the center of mass in the X direction to the right. Like I have more mass over here. It's gonna shift it over. So we still have to account for it. Yeah. Yeah, dude, summing up all the X positions times the X position of one object times I just says object one, object two, object three, it's what we're summing. Yeah, I kind of have stopped putting it here, but that's technically what a sum is. So like there would be xi if x position of object one, mass of object two, but like x position of object two, that now I just goes up to yeah, this is not like the control or anything like that. It's just there's like loops and indices what you that's a great point. When you are building this, you're not just summing up the ones on the x-axis. You're not just summing up the ones on the y-axis. You are summing up all the objects regardless of where they are. When you do this, you're adding up all the... How many objects are there? 3 objects. So your sum better have 3 things getting added together. On the bottom here, you better be adding up all 3. It's every object, regardless of where it's located, better show up in your sum. And that's true of x and y, regardless of where they are. The reason I mention this, I see this quite commonly. I totally get where the mistake is coming from. You are adding up all the objects. If there's 15, I don't care where they're located. You're adding up all 15. That's the key here. So I'll do it for one of them. x1 times m1 plus x2 times m2 plus x3 times m3. All of them. And then do it for y.
So I'll do 3
Well,
Yes, that's what I couldn't get. Yes. Yeah, it was like I know.
Be consistent. It doesn't consider mass. It doesn't matter whether it's consistent. And the reason is you
I would have like that's not good use of my time.
And the reason is this. I mean, if I just look at your board, 1.2 second 4.7 years is. And the reason all we're math is the units all cancel out. You have to adjust.
Oh, yeah, I didn't want it. I finished my card and then I literally
Why was Tom?
Because your average. So That's
He's trying to sort of realize once that
Yep.
So that's
For the Y? What's your Y coordinate? Those are, you put in a bunch of X coordinates there. Oh, sorry. Well, yeah, show me, point to which one's your Y coordinate one. Oh, the top one. Okay, I'll do the other one. Yeah, it should. Did someone just put one of your plugs there? You have plug numbers weird somewhere. Your setup is good. Yeah, go ahead and plug 0.225 divided by 0.325 in the calculator. Yeah, okay, so something. Go ahead and multiply 3 times 0.07. Your setup is good, something went wrong. Oh, yeah, that's fine. That's in centimeters. You did your whole problem in centimeters. So you need to convert it. Alright, so I'm just going to show you all just the X one, and I'll leave the Y one for you. That way I don't do all the fun things for you. So I'm just going to solve the X center mass. It's going to be the X position of object 1 times its mass plus the X position of object 2 times its mass which is 0.1 plus the X position of object 3 times its mass all divided by all the masses. 0.075, well, I'll put them in the order. 0.15 plus 0.1 plus 0.075. If you plug that all in carefully, you should get negative 0.0123 meters. If you got 1.23 centimeters, that's the same exact number. That's the most common thing I've seen is that people left everything in centimeters. That's fine. But your final answer is in centimeters then. If you leave everything in centimeters, this only works for center of mass. Do not in other problems keep everything in centimeters. Do not in other problems keep everything in grams. Center of mass is special in that if I have a bunch of masses on top and they're in kilograms, I divide by mass on bottom. If I have kilograms on top and I have kilograms on bottom, the mass cancels out. And then you're only left with the positions. That's why it doesn't matter what units you work with, as long as you recognize that. But pro tip, if that doesn't make sense, if you don't know why it doesn't matter that you convert, always convert it. It's better safe than sorry. Because what you do not want to happen on a test is ask yourself, wait, do I have to convert for this problem? And then you're unsure, and then you decide, oh, I don't need to, and then you did need to. Just always convert. That's a safe option. Make your life easier. Make your brain not have to work as hard. Give yourself one less thing. If you intuitively understand why you don't need to convert here, great. If not, just convert. Okay. Great. This is just a quick check to see if center mass idea makes sense. If the 75 gram mass was instead 6 centimeters, and you can see through the power of stretching my picture, I made it. What would happen to the X component of mass? And then we'll jump into fluids for like a tiny, tiny bit, and we'll start our lab after that. We only got like 20 minutes before we need to start our lab. So yeah, if I stretch the object, the 75 gram object upwards, what happens to the X component of the center of mass? Does it shift to the right? Does it shift to the left? Or does it stay the same?
I know it's not right?
Upwards, X and Y. Back to your like that. What is That's the purpose of this. See, hopefully as time goes on, you have like 7 minutes that like you're just cool with X, Y, where A is class here. Then you're like, why is All right, 10 more seconds. And 5, 4, 3, 2, 1. All right. Let's just look at all the answers and see how we did walking around. Oh, look at that. This is a question of, do you understand X, Y independence? Do you understand that X and Y are separate of each other? I changed the Y coordinate, but who cares? It doesn't affect the X coordinate. X and Y are independent of each other. It's a very, very important thing in physics, and this problem gives you a nice visual of that. Great. Okay. So, at this point, I am going to start, we're not going to jump to the lab yet. I'm going to start talking about fluids very, very minimally. Again, I think fluids are super, like going through this, maybe not, you'll find it interesting. This PowerPoint is going to have a decent amount of equations, but they're not bad equations. In fact, let's jump over the formula sheet. I'm going to show you all the equations because I don't actually have them, a nice list of them here. Oh, wrong one. Alright, if you all go to the formula sheet, I have updated the formula sheet with all there is 5 equations for fluids. And we're going to do practice problems for each example. Now the first one I really hope that you all have seen before. Its density is mass over volume. We're then going to learn about pressure, and basically that's going to be the name of the game. And then what's kind of interesting at the end is there's a conservation of energy. Hopefully this equation, you're like, some of the letters look a little different, but hopefully you kind of recognize what this looks like. It's not kinematics. What is a 1/2 times something squared? It's an energy. Yeah, it turns out there's energy for fluids as well. It's called Bernoulli's equation. And yeah, it's just energy. If y'all are cool with energy, you'll be cool with this last equation. The one that looks the grossest is literally just conservation of energy, but for fluids.
Are we going to know about the Fresnelli's?
Fresnelli's. I think that's just a variation on this, right?
Yeah, it's very.
Yeah, this one covers it all. There's another fancy name where basically one of these terms goes to 0. All right. So I got a big old laundry list of things we're going to go through because, again, there's a bunch of equations. We're going to talk about density. We're going to talk about pressure and its relationship between, not pressure and force, area and force. We're going to talk about how pressure varies with the depth in a fluid, Pascal's principle, Archimedes' principle. There's a lot of names here. A lot of, people discover things that get it named after them. Between velocity and cross-section. And my hope, if you all go through the fluid stuff, there's a decent number of problems in there that are within a medical context. So I got one with an eyeball. I've got blood pressure. I've got a syringe. There's a lot of applications to medical practices. The last problem, well, there's a couple here. Blood passes through capillaries and how velocity of the blood changes. And then an echocardiographic exam. It's got way too many compound words in here. I always forget that one. But this last problem is literally how they calculate echocardiac. Okay, and you are going to know way more about this than me. This is just my quick search. Is used to determine the pressure within something in the heart, I think. And this is literally how they do it. They measure the velocity of a fluid and they apply Bernoulli's principle to calculate the pressure. So that's why I gave this problem. It's literally how an echocardiographic exam takes its measurements. Anyway, so how much do I want to go through things? Yeah, this is the Yeah, I'm gonna get through this. I want to get through this and pressure, and we'll see if I can do both. I don't know. Yeah, so this is the classic. Like goodness, I think they asked this question. I don't know where they asked this question in physics, chemistry. Like, it's a classic. What weighs more, a ton of bricks or a ton of feathers? Does a ton of bricks weigh more? A ton of feathers are they the same weight? Whatever you think, put your answer. Well, I guess a classic. A ton here is a measurement, not like a description. A ton here is a measurement, not a description. Right? Yeah. You all seen this one before? Yeah, it's like, what class? High school something, biology. Yeah. All right, 10 more seconds. In 5, 4, 3, 2, 1. Ba-doop. All right, let's see if you all have seen this question in high school, middle school, something else. Yay, you have. It doesn't matter what the object is. If you have a ton of it, a ton is a measure of weight. What is different about a brick and a feather? What variable is different? Well, the mass of one individual object is different, and then the volume is different. The density was, whatever, that was the goal, whatever, it's fine. They have different densities. You need a lot more feathers. They have a picture of this, which I probably should have stolen. If you all made if you saw a ton of bricks, it'd be a nice little pile of bricks. If you had a ton of feathers, it'd be like some stupid giant pile. Because they have different densities. The variable for density is rho. It's the Greek letter. It's a P without a little, it's that. Greek letter rho. What's the capital Greek letter rho? I have no idea. Let's find out. It's just a capital P. That's very disappointing. All right. Great. So they've, English letters, a lot of it came from Greek. Well, some. It's all mixed together, y'all. Greek and then Latin, and those are mixed at whatever. It's awful. Anywho. Okay. Density. Now, there is something very important down here that's going to be a common trend in this PowerPoint, and it's kind of annoying. A lot of the variables we're going to work with have different units that represent the same thing. So like density. Density can be measured in grams per centimeter cubed, or kilograms per meter cubed, or grams per milliliter. And it's a little bit of a pain. When we talk about pressure, we're going to have pascals and millimeters of mercury and newtons per meters cubed. And yeah, there's a lot of different units for the same thing. Why is there so many different units? I have no idea. People don't like, I guess, meters cubed for some reason. When you go to this grocery store, no one wants to buy a 0.001 meter cubed of milk. They just want to buy a liter of milk. That's probably why. But fun fact, this is really cool. I didn't realize this. We've been working with metric units like a meter, a kilogram, all that jazz. Something really interesting that you find in this is that all the metric system was originally defined so that 1 gram per centimeter was the density of water. Like that was kind of the standard that then all the units were kind of then evolved around. It's not because they found in a wall somewhere that the density of water is 1 gram per centimeter cubed and all that. Someone made a decision. Water is going to have a density of 1. And then every other unit was based upon that. Everything was based upon that. It's not like water is so special that somehow, some way it magically, no, they chose it to be 1. And then everything else got based upon that. So just an interesting unit thing. Now, again, you got to be super careful here, y'all. 1 gram per centimeter cubed is not 1 kilogram per meter cubed. That's a really classic mistake that, like, you're going to want to probably do at some point. 1 gram per centimeter cubed. You're like, oh, I'm converting grams to centimeters. Kilograms are bigger. So that's going to be, they're like, the effects are going to cancel. They do not cancel. That is not true. Yes, a meter is bigger than a centimeter. Yes, a kilogram is bigger than a gram. But, like, let's just go through this real quick. This seems like, why am I doing this? Because you will make this mistake. Someone's going to make this mistake where they say 1 gram per centimeter cubed is 1 kilogram per meter cubed. How many grams are in a kilogram? 1,000. So if I want to convert this to kilograms, so 1 gram per centimeter cubed, we're going to do the way that I've seen you all do it, which I like. There is 1,000, well, we got to do it the other way. For 1 kilogram, there's 1,000 grams. So we're going to divide this by 1,000. Okay? How many centimeters are in a meter?
100.
100. There is 100 centimeters per meter. And here is where you have to be extra careful. It's centimeters cubed. So you don't do this unit conversion 1 time. You don't do this unit conversion 2 times. You got to cube that unit conversion. If it's centimeter cubed to meter cubed, I got to convert centimeters 3 times. And if you do that math, you will find that 1 gram per centimeter is 1,000 kilograms per meter cubed. And this is also something that's very easy to check yourself on. If you say this is true, if you all say that this statement is true, 1 gram per centimeter is 1 kilogram per meter cubed. Literally, let's think what the logic of this means. If you have 1 centimeter cubed of water, a cube, that's 1 centimeter. If you have a cube that's 1 centimeter, my cube here is going to look terrible, but wait, oh, it's okay. All right, I'm actually happy with that cube. That's my little cube of water. If I have 1 centimeter by 1 centimeter by 1 centimeter, all these are centimeters. What's the mass of that cube going to be? 1 gram. That's the whole point of density. However much you have, that's your mass of it. If I have 1 centimeter cubed, I get 1 gram. If you have a box of water that's a meter by a meter by a meter, that's a big box of water. Way bigger than this. I don't think I can quite draw it to scale, but you all got a giant box of water. It goes off the screen because it's so big. If you tell me that 1 gram per centimeter cubed is 1 kilogram per meter cubed, you're telling me that that giant box of water weighs 1 kilogram. 2.2 pounds. A thing of water this big weighs only 2.2 pounds, and that's not true. That's not true. In fact, something that you all might not realize is how heavy water is. 1 meter cubed of water. If you literally just grab a meter stick, make a box, a meter by a meter by a meter, it's 1,000 kilograms. 1,000 kilograms is 2,200 pounds. Water's really heavy. Like way heavier than you all. Yeah, it's 1 meter by 1 meter by 1 meter is literally 1,000 kilograms, which if you convert it to pounds is about 2,200 pounds. It's heavy. This is why tsunamis are so dangerous. This is why when water levels rise, incoming water, if there's a big wave of water, even if it's only a tiny little height, it can knock you over really easy. There's a lot of mass behind that. Yeah, it's nuts. So there's lots of consequences of that. But anywho. So let's practice this. Water has a density. Where'd it go? Water has a density of 1 gram per centimeter cubed. How kind of me to give that to you. What is the mass of 230 milliliters of water? I will also tell you 1 centimeter cubed is 1 milliliter. They're the same thing. Again, there's lots of little things here. 1 centimeter cubed is 1 milliliter. 1 meter cubed is not 1 liter. Do not. That is not. Again, if you buy a liter of milk, it's not a meter cubed of milk. Yeah. They do not work the way your brain might want to intuitively jump to.
And then I have grams of question, and I have 2
So do you want it to equal 1 still?
1 equals
230 milliliters equals 230. Yeah.
no.
So do you want it to still equal 1? Like, could you find her? For these two, you still want it to equal because that's like the density. So like would we find the number on the top of the one?
So right now, what are you solving for? That's the question.
The mass you're solving for the grams.
So how many grams is it?
Oh wait.
Yep, that's it. Yeah, that's all this. So that's one way of doing it. Just kind of what you wrote there. You can kind of see that from, yeah, you have, if 1 milliliter is 1 centimeter cubed, you have 230 of them, then you have 230 grams. And yeah, that's, we can use this equation to also do that. Density equals 1, volume equals 230. 1 times 230 is 230 grams. 230 grams is 0.23 kilograms. All right, give y'all 10 more seconds. And then as much as I want to keep solving problems, we'll probably stop after this one. As much as I want to do the next problem today, we'll wait. All right, so 5, 4, 3, 2, 1. Ka-chow. So the easiest way to do this problem, in my opinion, so you write down your givens, you got density, you all have volume. What are we solving for? That's always the goal. We're solving for mass. When it comes to fluids problems, they are going to be very much what's given, what am I solving for, what equation. Like they're going to be very, very chemistry. I feel like a lot of chemistry math is kind of the givens missing. Maybe I'm wrong, but whatever. So great, we're solving for mass. So you have density equals mass over volume. You can rearrange that. That mass equals density times volume. So mass is going to equal 1 times, and this is something I'm also going to point out, this is 230 centimeters cubed. So the thing you really got to be careful of when you're working with fluids is making sure you're working within units that play nicely with each other. Do not play with grams per centimeter and then a separate variable have meters cubed. Or do not have milliliters and then kilograms somewhere else. Your units got to play nice. So in this case, when we're working with fluids, I might actually for once put the units in my equations to see that they work nice together. The centimeters cubed cancel, and I get 230 grams, which is really easy to convert to kilograms. Yay. That's one way. You could have also done a thing where you converted milliliters to meters cubed and the other one to kilograms per meters cubed and gone through all that. It all works. Okay, I'm going to point out the next problem, but we're not going to solve it for the sake of time. So the next problem, we're going to find the density of a gas can filled with gas. Crazy, right? The reason this next problem, though, is going to have a little bit of complexity is we're going to find the density of both of them together. The gas can has some mass and some volume. The gas has some mass and some volume. What's the density of the combined system? Why is this important? Your body does not have a uniform, like it's made of a bunch of junk with varying densities. So if you measure the density of a human body, it's not the density of bone, it's not the density of fat, it's not the density of muscle, it's the density of everything together. And so this next problem will kind of show us how do you calculate the density of something with everything together. If you were doing a human body and you wanted to measure the fat percentage in someone, you would actually stick them in water. One of the ways to do it is hydrostatic testing. You stick them in water, not hydrostatic, whatever. You stick them in water, you measure their density from that. We'll do a couple problems on that. And then you actually work backwards with the assumption of how much bone someone has in their body, how much muscle mass. And they can then guess how much fat percentage someone has. That's one way of doing it. So anyway, that's the problem. I give you the mass of a steel can. I give you the volume of gas. And then I give you the densities of the two. And we're actually going to have to do a few steps. It's probably not a one and done problem. There's actually a couple steps here. You got to find the mass of the gas, the volume of the gas. You need to find the mass of the steel. You need to find the volume of the steel. And then we'll put all of those together. All right, whatever. That's next time. Take a breather. You all got, we'll say like 4 minutes, 5 minutes. That way we can jump into the lab.